It's a pleasure for the last for the talk of the day to have André Belotto da Silva from Paris, who is going to talk about splittable foliation and the minimal rank Sard conjecture.
Okay, so first of all, thanks a lot for the invitation and the opportunity to talk a little bit about mathematics that I do. Thank for the organizing committee, all of you. So I'm going to talk about like the main point would be an application actually to differential geometry. So I'm not going to assume which is what we call the minimal rank Sard conjecture or the Sard conjecture, which is a little bit stronger than I'm going to talk about. So this is a conjecture in differential geometry, in sub-Riemannian geometry, but we're going to work with it in the hypothesis that we have at least the analytic category, maybe even algebraic, or like I'm going to ask a question about it. And the talk has three kind of parts, which I'm kind of going to invert the order in some sense. So the first part would be to present the Sard conjecture and state the main theorem that we have, give an idea of the proof, and the theorem that we're going to state, the hypothesis is going to be this condition of the splittability, and then talk about it. But when I was preparing the talk, I always kind of pass it a bit 1 hour. So since I want to have time to actually talk about, like ask my question in a precise way, I'm actually going to start with maybe the most technical part without the motivation, and then I'm going to motivate why I'm asking this question, okay? The condition that I'm going to give. So this is going to... No, that's that's exactly the opposite of what I wanted. I'm going to start with 3. Okay, so I'm going to start with N is going to be a real analytic So starting, I'm going to work in the real case. Riemannian. So there is a metric manifold. And for now, we're going to see that it doesn't make much of a difference to have a singular set. I'm going just to take F, a regular analytic foliation. Of rank equals to D, some rank D. And I want to study a property of returns of leaves in some sense. So if this was a vector field, then I could actually talk about returns. So let me just, in the general case, let me just be a little bit more precise. For every x in N, I'm going to denote by f of x the leaf, which contains x. And I want to understand the points which have distance inside the leaf of a fixed length. So I'm going to take let L bigger than 0. I will consider an x and y 2 points in the leaf. Then I'm going to say that they are L related. So x, y are FL related if their distance through the leaf is smaller or equal to L. So if, what does this mean? If there exists a curve, right? 0, 1, which goes to f of x, absolutely continuous, so that we can compute length. C of 0 equals to x, C of 1 equals to y, and the length, which we can compute since it's a Riemannian manifold of psi small a equal to L. And as we're going to see, what I want to do is a property of return. So I want to have finite number of returns with a certain length. So the property that I want to study, which I'm calling splittability, I'm going to say that F is splittable in And with the metric that we have fixed, if for every point, so there's a lot of quantifiers. So for every point of n, and for every transverse section, local transverse, which contains x, and for every L. Now there's an extra condition here, but I'm going to just jump it and just give the first part. So I want there to exist F Algebraic measurable set which is going to be contained in this transverse with positive volume in respect to the dimension of the transverse. So this is n minus the rank of the foliation. This is going to give us the dimension of the transverse of F has to be positive, such that for every 2 points in F, they are not, Y and Z are not FL related. Right? This is the condition I want to, in every point of this transverse, to find it, some subset where, at least with this length L, I cannot connect 2 points inside of F. Sorry? What is what? Sorry? Transverse. Local transverse. Section. Huh? Sorry?
What is it then?
It's just a submanifold closed, which is at every point is going to, the tangent space is transverse. So the sum with the tangent space given by the foliation generates the entire space, and it's also, the intersection is also trivial. Okay. So there's, maybe I can just say, H is the metric. So it's a property that depends on the Riemannian metric that we're going to put. So I'm just saying that because it depends on the distance. Okay. So I'm going to complete what I'm going to put here, but it's kind of somehow not as important for the first part. So I'm going to keep it open for now and just explain with an example what we're looking at. So a typical example is we take the torus. Let's just take R2 and let's quotient it by Z2. We take the torus. I'm going to take, I'll take this so that I can take T. As a transverse, I'm going to take this part. All right, so this is just 0 times 0, 1, which is just homomorphic to S1. And the foliation that we're going to consider is just some irrational foliation. Some line foliation with an irrational term. So just say the differential of y plus or minus square root of 2 times x, right? So this gives you a foliation here. So this is our transverse section. It's going to be transverse in that sense that I just said to every one of the leaves. So if I start here, I'm going to have some slope. And then I will come back here. So in this case, if I have a vector field, if everything is real, so I can have a choice of vector field, I even have a return map. Right? So in this case, what I'm trying to do is to find some subset of T, which captures at least 1 point of somehow each orbit when I intersect with T, but with a finite length. So of course, if I try to do this without the finite length, this is not going to work, right? So let's just imagine that if I take F, so first remark here. if I take some point y0 in T, then the leaf f of y0 intersected with this transverse. So if I just move along and then when I come back, I'm just summing the square root of 2 or subtracting and taking mod 1, which is the action, right? So this is going to give us as a set, well, y0 plus k square root of 2. And that's it. For k, mod 1 for k in z. So maybe this is kind of a standard thing, but I'm going to do the computation anyways. If we try to take just one point of each orbit or of each one of these intersections, so let f, or maybe I'm going to give it as a g, 1 point, a set containing 1 point of each orbit. It's a vector field. Then the claim is that it's not measurable. Right. So indeed, just to recall what can go wrong, right? If we take this G, then we can take all of the automorphism of the circle. Sorry, exactly one. Yes, exactly one. And we take all of the automorphisms with the K, GK from S1 to S1. They take Y0 and take Y0 plus K square root of 2 mod 1. Then we know that at the one hand, the T is going to be the disjoint union of all of the GKs of G for K in Z. So if it was going to be measurable, then the Lebesgue measure here of the transverse section will be also equal to the Lebesgue measure of the union of GK of T which since they are just rotation, so they are keeping the measure. So this is just going to be equal to me of G times the sum of 1 in K over Z. And here you're going to get a contradiction anyway that you want. If it's 0, it's going to be equal to 1. And if it's positive, you're going to get infinity. So it's not going to be 1. So contradictions. Contradiction is with the fact that we were able to write me of G here. Right? There's no Lebesgue measure there. But of course, if we take some finite length, then we're able to do this. If we take some length, for example, which is smaller than square root of 3, which is the size of in order to return, then you can take T, all of it. And if you take something which is bigger, you just need to take a very small, sufficiently small subset of T. So say, for example, if L is equal to 2, we may take F equals to 0, 3, for example. That is good enough. So in this case, there's only 2 returns. Either you can go with +1 or -1. And then you can make the computation. This is an example here, that if you just move either with +1, square root of 2, or -1, you're only going to get things which are disjoint. And this kind of idea you can do for all L. So here the idea, actually, we can prove some sort of lemma that if F is rank 1, then it is splittable. And the idea is that given this transverse section, you can have local flow box theorems, right? The selectionization, as Column showed, you have the transverse. You have a local chart where your foliation is going to look like this. And in that chart, you have that the length is going to be at least over that chart. The length is going to be at least some epsilon. So there's only going to be at most L divided by epsilon, or 2L divided by epsilon points in f of x intersected with t, right? Because we have to get out of the system of the neighborhood and to come back somewhere else. So this is the property that that I want to study, and the question that I want to ask is under which conditions this is satisfied. For example, if I have something which is on a projective variety, an algebraic foliation, is it always true that it is going to be splittable? And that's my question. F analytic is splittable. So in order to say a little bit about what I'm searching and what kind of behavior I want could go wrong, I want to just present an example, which is kind of abstract, but an example of a foliation that does not satisfy this. And then I'm going to give you the motivation for doing this. And also the framework that we work. So the foliations that I'm actually interested in, they're going to come from, they're going to be characteristic foliations. So there's going to be many more constraints. So the question as I'm asking here, actually the foliations that I'm going to care about, they're going to have other constraints that I'm going to present later on. But for now, even just having a foliation which is algebraic in a projective variety, like we can define everything in the singular space with singularities of f, just by defining the same thing outside of the singular locus. You can get the same kind of definition. Okay, so this is the question, and let me give you an example of something which is not explicable, but it's quite it's abstract. So it's a modification of a foliation by Hirsch. Right. Hirsch foliation. So, sorry? Sorry. Thanks. Thanks. Yes. Okay. So the building block of the construction is to take a torus. So I'm going to take a plane torus. Sorry about this. And he was my collaborator, so. And what I'm going to do is I'm going to take away a torus from inside. But I'm going to take away a torus from inside so that I do a double loop. So I'm going to take away a torus that does like this. So here's an S1. I mean, I'm gluing this part with this. You have to imagine that this is the torus. And here we come down, come here. And this one comes there. Okay, so I took away this part. And now, as the foliation that we're going to see, I'm going to project it into S1. And I'm going to look at the fibers. So the fibers are going to give something like this. So it's just a disk minus 2 disks, right? So these are topological pens, right? The fibers here, the fibers. And I like to think of them as topological pens. So I like to think that if I take this V, which I'm going to write it here, I'm going to write with V0, the leaves of them are going to look like this. And as a transverse section, I'm going to take one of the S1s, which are inside here. So I'm going to take something like this. This is going to be the transverse. So one of the things that it is transverse to every one of the leaves, but it cuts twice each leaf. So if I look at them from the point of view of the transverse, each point meets twice. So this point, this leaf here meets twice this section. And then what you do is that you glue this, you glue several of this construction. So you go ahead and you build another one here. So you continue this process. So let me give it I did not do this right. So you continue this process. And you glue these leaves with another topological pen. So this is going to give you an analytic foliation over this abstract manifold. You have the transverse section. So in the first round, every point was linked with just another. But when I go to the next one, then I'm going to be linked with 4 of them. And if I go another time, then I'm going to have 8 points. So what you can see is that the leaf that I started here, so if I take f of x and I intersect with this transverse, this is just going to give me something of this form, y2, y0 plus m divided by 2 to the power n mod 1 for n and m. Z. Well, yeah, it's clear. That's good enough. So you have all of this. So again, you have the problem that you cannot choose one point of each set, because this is not going to be measurable. It's the same kind of issue. And now what you can do is that you can glue metrics here too. So you can produce a same infinity metric by just asking that at every one of these building blocks, the geodesics that go from one point to the other here are of length at most 1/2, 1/2n indexed here by this part. And if you do this, then all of these points are going to be connected by a geodesic of length at most 4. So this is going to give you something which is not splittable. But I'm not talking about what happens in the somehow it's not compact, right? I mean, I'm introducing a metric. I'm not getting something which is compact. So I'm not telling you what happens in what is supposed to be the singular set. It's kind of the limit of it. So that's why this is an abstract example. And I think that's why my question is under which conditions, and maybe over just looking in the Rn, we're going to be able to exclude completely this property.
So
always have it.
Gluing 2 examples to think of that, you glue exterior boundary with interior boundary.
Exactly. I glue this with the exterior several times.
But then here the metric is not complete. Even
Not complete, yeah. Yeah, the example is not complete, yeah. So I'm going to keep this definition here.
And why you left so much space here?
Because I want to add when in the end of the talk, what is the other condition, which actually I don't feel it's important to understand what the condition is, but just when it comes to it. I wanted to simplify the talk, but I didn't want to lie. So I'm making sure that I am omitting something. So now let me talk about the motivation for this. And the motivation, I'm going to give you a theorem, which is the theorem that I actually care about, and then I'm going to spend a lot of time defining what are the objects of the theorem. So the theorem, the reason why I'm interested in this is that myself so here's going to be the setting that I'm interested in. Let M be an analytic Riemannian manifold, everything real. And now something that I will define, delta, an analytic non-holonomic distribution. And now the conditional statement is if another object that I'm going to define just now, if the sub-Riemannian characteristic foliation F tilde F is splittable, then the minimal rank Sard conjecture holds true. So I'm going to spend some time talking about what does this hypothesis mean, where does foliation theory appears. This is going to give us extra constraints on the foliation that we're looking at. Particularly, it's a characteristic foliation, so we know that it's going to come from the kernel of a symplectic form. And then I'm going to talk about what is this minimal rank Sard conjecture. So what is the application to differential geometry?
You mean minimal rank Sard conjecture for some of the objects above, right?
Yes, for these ones. Yeah, for M and delta. So this guy satisfy the minimal rank for. So I'm going to present things and I'm going to simplify a little bit the talk. I'm going to simplify by assuming that delta, which is a distribution, so it's just a fiber, like for every point you're going to consider a subspace of dimension of some constant rank R, but I'm going to assume that it's corank 1. So for the talk, I'm going to assume corank of delta equals to 1. So in this case, what is delta analytic non-holonomic? So first of all, delta is locally. So here we can assume n equals to some Rn. Delta is going to be spanned by n-1 vector fields, which are analytic. And the condition of being non-holonomic means that if I take the Lie brackets of all of them, then I'm going to generate the whole tangent bundle. So this is, to some extent, the opposite of being a foliation, right? I'm taking all of the Lie brackets and I generate everything, so I don't have leaves. So just to give a kind of the local sort of feeling, you can imagine locally again. You can always suppose that you have this kind of situation. dxn n-1 dxn-1 an-1x delta xn. And that when I take the Lie brackets, so not just once, I'm not talking just about contacts, contact structures, if you know, yep. I'm not only talking about contact structures. Maybe I need several Lie brackets in order to generate everything. Okay. So these objects here are the objects that are studying in sub-Riemann geometry. So what people are interested in sub-Riemann geometry is to study orbits or trajectories, the curves, which are everywhere tangent to them. So you have some constraints, you added some constraints on the paths that you can take, and you want to study the geometry of these paths. So what is called horizontal path are absolutely continuous curves. Absolutely continuous just means that you can compute its length, which is finite because it comes from something compact, such that whenever you can derive it, it is in the distribution. So whenever you can derive it, it is there. And there's the classical theory of this theorem, of this theory, sorry, says that the non-normicity condition implies that, provided that M is connected, provides that M is path, horizontal path connected. So you can go to any 2 points via such an orbit. Therefore, you can talk about geodesics. Like it's a classical problem in this theory to understand the role of geodesics. But I'm not going to explore too much this side just yet. I'm going to talk just a little bit, but I'm going to focus much more on the geometry of what we need. So I want to say, where does the foliation appears kind of right away. So let me tell you about the characteristic foliations. So the characteristic foliation, we're going to work in the cotangent bundle, Tm, which I'm going just going to think as T of Rn here, everything local. And I'm going to take the symplectic form, therefore, omega equals to dxi dpi, where x and p are the coordinates of the cotangent bundle, the usual coordinates. And I will take the usual projection, canonical projection to M. So an important object in sub-Riemann geometry, as we're going to see, are going to be some special. There's going to be some special of paths, which has a characterization in the cotangent bundle. So I'm starting already with the geometry that we will need to give this characterization. So what are the objects that we're going to look? We're going to look at a subset of the cotangent bundle, which is given by. So let me see how I wrote this. Yep. The xp in, let's say, Rn, well, M, such that, well, I want to exclude the 0 section, and p times v of x equals to 0 for all v of x vectors in the tangent, in the distribution at the point x. So for every one of these directions. So this is going to be the annihilator. So in the cotangent bundle, the annihilator of the distribution delta. Okay. So I'm going to take this as a subset. And the characteristic foliation is foliation is the following. There exists an analytic foliation or better, let me state it in a different way. if I take the kernel of the symplectic form restricted to this subset, this will generate an analytic foliation F with singular set sigma, which are the points where this kernel has, so there is a big open-dense set where this kernel has constant rank, and then you have the points where the rank changes, and this is going to be the singular set. Singular set sigma contained in here. So this is the characteristic foliation that we were talking about in the theorem that we presented here. So if I come back to the example, this object here, they're just going to look. So if I take these equations and I multiply by p, what I'm saying is that these guys, they're going to look as the zero sets like this. N equals 0 with p difference from 0. So first remark, the dimension in this case, when the dimension is correct of delta is, with the corank of delta is 1, and the dimension here is n plus 1. The first thing. But there's another thing that I feel is important here to note, which is these are all invariant by dilations in the direction of p. And so is the symplectic form. So actually, both of the objects that I'm talking about here, the characteristic foliation and this set, they could be defined over the projective cotangent bundle. And F may be defined over the projective cotangent bundle. So this means, and this is why I'm also simplifying with corank 1, because then I have a very nice picture. This observation combined with this one means that I could actually project this foliation over M. We have M, P, and what I'm saying is that since it is going to be invariant by the dilations, the dimension, which was n plus 1, is actually n. So I'm going to have some singular set here, sigma. Then I'm going to have the foliation. And actually, one could project this foliation there. And the projection of sigma is also a proper analytic set. Yeah, okay. There's going to be a gap in the definition. That's no problem. And the last remark that I want to make, which is going to be later used, is that since it's coming from the annihilator of a 2 form, we know that the difference between the dimension and the rank of F is going to be even. So dimension, so n plus 1 minus the rank of F is equal to 2 times S. So let me just say now very quickly, why are we interested in these characteristic foliations? And what is the Sard conjecture? Unfortunately, I do not have enough time to really give a feeling about the theory that is behind and what people care about this conjecture. But at least I want to state it in a kind of precise way. So there is the notion of singular horizontal paths. So the heuristic is that if you have an horizontal path which is not singular, then you can use Riemannian techniques to study them. But there are some special horizontal paths which do not appear in Riemannian geometry, which we are going to call them singular, and therefore we have to study them via different methods. So there is a characterization here due to 2. That says the following: a horizontal path gamma horizontal is singular if and only if it admits a lift. There exists a lift. So a lift means that the projection to M is going to be the gamma and P of T, which belongs to gamma, to the annihilator. So something which belongs to the annihilator, and C prime belongs to the kernel of the symplectic form, restricted here, for almost every T. So whenever it's differentiable. So this gives you a characterization of the singular horizontal paths, which is purely geometrical. So I'm just looking at this characteristic foliations, and I want to be able to, like, the paths that I'm going to be interested in kind of studying, that I have to study in a different way, are the ones that when I lift like this, I will be now tangent to this new foliation in the cotangent mode. Now I'm saying that these paths, they create a problem for the theory in the sense that you cannot study them via usual methods. So you cannot adapt techniques from Riemannian geometry directly to sub-Riemannian geometry exactly because of the existence of them. So one of the conjectures of the field is that they don't kind of matter too much, at least if you're doing measure theory. So what does that mean? That means that if we take, let x0 be a point of n, and let's consider the set of all points that we can attain with one of the singular paths. So these are y's in M. We can pass by via singular horizontal path. So just to say, this set is also, so I didn't have time to define, but just to make the parallel, this set is also the critical values of a certain map. Called the endpoint mapping. Right? And they are contained in M. So the conjecture is going to say that at least from a measure perspective, the number of points that we are going to arrive with these problematic orbits are going to have measure 0. So Sard conjecture. For every x in M, let's say the volume here is equal to 0. That's the conjecture. In the case of corank 1, so that's also why I'm doing this, to assume that it's corank 1. Sard conjecture is equivalent with what we're calling minimal rank. So for the talk, it's enough to have this result, to state it like this, at least for understanding what we're doing. So just a couple of phrases about the literature. Yep. So there's a strong version of this in dimension 3. There's a strong version. Which is that for every A, every X in M, so everything in dimension 3, then the house of dimension of the set is equal to 1, is bounded by 1. And the results in the literature, they are known, are the following ones. So for dimension of M equals to 3, Zelenko and Zimtorsky prove the strong version, strong, in 95, under the hypothesis that M and delta are generic. And then myself, Gali, Paruzinski, and before prove the conjecture, the strong version when M and delta are analytic. This is kind of the first step to try to understand the full conjecture is you start with the smallest possible dimension to try to understand it. And in higher dimensions, there's very few results known. So basically the best result is a result. So there are many authors, so I'm going to just write Ledonné, Montgomery, Otazi, Pansou, and Vitoni in 2016. They proved this conjecture for a class of examples, which are called Carnot groups. Of either the rank of delta is equal to 2 or the rank of delta is equal to 3, and what is called the stack. So the number of Lie brackets that you need to generate is smaller or equal to 5 or smaller or equal to 3. So besides these examples, the conjecture is open. So, and our result is this conditional result. If we know that this characteristic foliation is going to be splittable, then we can get at least the minimal rank Sard conjecture, which in the current one case, it's the same as the Sard conjecture that I'm presenting here. So that's why I'm interested in answering the question that I made. If we could get rid of the hypothesis, this would be a positive result for this conjecture, at least in the analytic case. So now, I just want to give us some ideas of the proof, so that we enter the definition of splittable. So it's a proof by contradiction. So suppose that there exists some point where these guys have volume, positive volume. So what does this mean? This means that, well, we have something in M here, which is of positive volume containing this XX0, but we could look at it over here. And since everything was invariant by dilations, and this guy was dimension n+1 invariant by dilations, so the Lebesgue measure 0 here set is going to generate a Lebesgue measure n+1 set contained here. So we can argue completely by contradiction over this set. We have the sigma, and we know that we have to follow the foliation in each one of these points. So I cannot go for one leaf to the other via a single horizontal path by leaving the foliation, right? The only way for me to go from one leaf to the other is to go to the singular set with a finite length, move along the singular set, and then return. So let me do this. So like this. I have the singular set here. So this is a representation of this guy. And what I'm saying, I'm taking this part here, V0, which is contained in the prime image of this guy, right? And in order to be connected, so I'm saying that in between every 2 points, I have the foliation. And what being singular horizontal, what being connected by them means that there exists a singular horizontal path from this point to this point. And I need to follow the foliation because I need to follow the characteristic foliation. So the only way, so if I just stay in a leaf, I'm going to have Hausdorff dimension equals to the dimension of the leaf. So I cannot do everything. So the only way for this to happen is that I will have to approach the singular locus, move along, and then come back. All of this with finite length. Okay, so what is the, so I'm going to actually work not with this V, but I'm going to work with a transverse now, with a transverse section. So what is the couple of observations here? So why did I say, why did I notice that the difference of the dimension of sigma perp and the rank of F was equal to an even power? It's because I want to use the symplectic form as a way to measure the transverse for an action over the transverse. So let's note, so this is a first remark, that if I have 2 transverses here, let's say T1, T2, so I have a region here, let's call it R, in between them. Then I know that the symplectic form, the differential of the symplectic form is 0. So I know that 0 is equal to the integral over R of d of omega s. Here's the exterior product of omega s times. And this is going to be by Stokes, the integral over dr, the border of omega s. But we know that the characteristic foliation, it has, the directions are in the kernel of omega s, of omega. So they are also in the kernel here. So everything that we are integrating on the over the leaves is going to be 0. So this is just going to be the integral over T1, plus or minus, depends on the orientation that we give, omega s. Okay, so once we have this first observation, then the idea now is to construct a sequence of transverse that approaches the singular set, and where we are going to keep this action. Why we're doing this? Because when we approach the singular locus, omega s, this form is going to go to 0. So I'm going to obtain a contradiction because I'm going to have something here whose action is non-trivial. And when I converge, the action is going to be trivial. It's going to be 0. For this, I need a property of the transverse. I needed to have bounded volume too, right? If the volume of it exploded, then I would not obtain a contradiction. The omega could go to 0 and it would not make a difference. So this we deal with via sub-Riemann geometry, so via subanalytic geometry. Existence of these transverses, sections, which we call, because we wanted to give a name, we call them witness transverse because they witness all of the leaves of the singular, of the foliation. And finally, what is the issue? Like there is something that this drawing is misleading. So far we are doing this argument, but there's something that this drawing is misleading. Why the transition is injective. So the drawing is misleading because in the way that I'm drawing, every leaf is cutting one point here and it's cutting on only one point of the next transverse. What could happen is that the actual, like you have two leaves here which cut at the same point, just as in the case of that foliation that we had with the torus. So if that happened, you can imagine that all of the action doing here is actually like you're doubling it here, so you're going to divide it by 2. So the action at every time that you pass is going to be divided by 2. And therefore, it's going to go to 0 without any contradiction. So I need a way to, with finite length, pass from one transverse section to the other in a form that is injective in respect to the leaves. And that's where we use that hypothesis of splittable. This is what guarantees for us that we do have the injectivity, and therefore we can use these two observations. So I'll stop here. Thanks a lot for your attention.
Are there any questions from here?
The missing condition. Right. Yeah. So the missing condition is that it's a proof by contradiction. So I cannot guarantee that all of the transverse is going to arrive at a singular locus. So the missing condition is that I need to add in that gap for every E measure containing T, Lebesgue measure containing T, Lebesgue measurable, with n minus d of E positive. And then when you say exists F, I want an F which is containing E. And then the rest is the same. So here, when I pass to this transverse, I cannot actually assume that all of the leaves in the transverse are going to arrive near the singular locus. By the contradiction argument, I can only guarantee that there exists some measurable set, some measurable subset of the transverse with this condition. So that's why I add this extra technical thing, which now I think it makes a little bit more sense to explain. Yeah. This was a missing condition.
So in case your foliation comes from the representation or the suspension of some automorphism, what does the splittable condition say?
So say it again. So the case that
our foliation is just a suspension of some automorphism.
So if there's no singularities and you are in a compact manifold, then you, am I saying something? Then you have then the curvature has a lower bound. And in this case, the volume with the same length is going to be bounded, so it's going to be definitely splittable. So if you're in a compact, if you don't have singularities, it's going to be split, and it's compact. So in this case, it should be good. And I'm interested in the question like algebraic, even complex to start with. If someone knows sources of this kind of transcendental behavior, I'd be interested.
Any other question? Oh,
Thank you.
Tomorrow morning, if you want to come just move for the walk, but doing comfortable shoes.